All right, so let's get started. It's almost 2:10. Okay, so this is lecture 3 on my side, and as promised, I will be talking about probabilistic cataloging. However, you probably realized that I actually skipped a lecture. Basically, I underestimated the amount of time we would be spending on dark matter by a factor of 2. And for astronomers, this is actually a good precision because we almost always make estimations that's good up to a factor of 2. But that's not an issue because I basically appended lecture 2 to the beginning of lecture 4. So I will be talking about probabilistic cataloging as promised, no changes in lecture 3. It will be mostly statistics. And then in lecture 4, it may be slightly crowded, but we will do highlights of lecture 2, and then because they were already connected anyways, we will just first talk about strong lensing and then directly tie it to the small scale structure in lambda CDM. So I think they will be causally connected in this way. So this was not by design. But anyways, let's start with now the idea of so-called probabilistic cataloging. Now, when I say this, obviously it may not mean anything to you at the moment, and that is totally fine. The idea is to discuss why, well, first of all, what it is, and then why we need it. Or actually, I will first motivate why we need it and then define it. So first, we will just basically talk about some fundamental aspects of inference, and then introduce the idea of probabilistic cataloging, and finally just talk about the implementation details, some implementation details and cross-checks of the relevant software that is called probabilistic cataloging, and that's PCAT for short. So I will start with inference now. So when I say inference, I think most of you will think about just mapping basically some quantity to some other quantity. So essentially, if I give you x and y, or if I give you x and tell you a mapping, then you can so-called infer y based on x via some transformation. In the scientific context, usually we replace these two objects with data and model. And basically, you either construct a model and so-called forward model it to project it onto the data space, or you start with the data, such as in machine learning applications, and find a transformation to map that into the model space after some prescription for what the model is, obviously. That mapping contains that prescription. So I will just use the capital D for data, for short notation, and for the model, I will have such a notation where M sub n will refer to the model of question under question with the subscript n denoting the dimensionality of the model. That is the key point here, because when you have a model, you have a bunch of free parameters, and the number of free parameters is a very important concept in what I will be discussing. So I will denote it with m sub n, and theta sub n will be the relevant parameter vector. So given a model, you are in an n-dimensional space, and theta sub n is essentially a vector in that space. In typical applications in science, we start with a really large data vector or tensor. It can be n-dimensional. If you are working with an astronomical image, it's probably 2-dimensional. If you are working, let's say, with an m-body simulation, it can be 3-dimensional. I don't know, if you are working with a light curve, it's 1-dimensional. And there might be basically composite data that contains some 2-dimensional, some 3-dimensional component, etc. However, usually it's got more dimensions than the model, and that makes sense because essentially science is all about dimensionality reduction. You try to go from large dimensions to small dimensions because that's what we actually mean by the word to explain. To explain is to actually take a large data set and just bring it down to, let's say, a sentence, or if you can do it, an equation. For example, an Einstein field equation is just 10 equations that can compactly describe petabytes of lensing data, gravitational lensing data. We will come to that. Yes.
The dimension of D is not the same as
No, it's like, well, it doesn't have to be. It typically is.
So n is, for example, for astronomical observations is equal to 2?
No, it can be anything depending on your model. We will come to examples. I'm very abstract at the moment. It can be anything, really. So there are two ways to do this. First, there's the predictive inference, where I think I mentioned this already. You go from the data directly to the model space. There is also generative inference, where you take the model and sample randomly and then project it into the data space. And a couple of important points here. I already defined forward modeling, the projection of the latent space of the model, that is m theta, using some prescription for physics. Could be Einstein field equations, could be Boltzmann equation, whatever. You forward model it, and you get the so-called m sub d vector, which has the same dimensionality as the data. So you can actually make the comparison. You can compare the output of your model with the data. And that comparison is contained in a statistical object called the likelihood. It's basically the probability of observing the data, D, under some model M. Okay? That's just the definition I will be using a lot. So that's basically the likelihood I already mentioned, and that's the notation for it. Okay, two more things just to mention. First, cataloging. Cataloging is essentially the inference of some model elements, and now you'll ask what an element is. Well, an element is the so-called identical subpart of a model. So, for example, imagine you are an astronomer. You are given an astronomical image. You are trying to fit for the positions and the fluxes of some sources in an astronomical image, let's say some HST Hubble Space Telescope image. Now, those elements are then just point sources. They are identical subparts of your model, and they have certain degrees of freedom, such as position, flux, etc., color. So that makes up your model, just to give a concrete example. Now, why become a Bayesian? Now, I will talk about why. First of all, I should probably define this. There are two schools of thought in statistics. One is frequentism, the other is Bayesianism. In frequentism, your definition of probability is frequency of occurrence. So if you, let's say, roll the dice a couple of times and then just look for the outcome, you can assign probabilities based on your observation, very observation. However, we do have many situations in life and science as well where you cannot actually do this because you cannot repeat the experiment. For example, sometimes you just have the so-called prior degrees of belief about systems, and you just have to assign a probability that you just cannot observe the occurrence of, such as the prior probability that tomorrow will be rainy, something like that. That you cannot really define in frequentism. So by changing your definition of probability to what we call degree of belief, you promote yourself from frequentism to Bayesianism, and there's a lot of intellectual property that comes with that, some of which I will mention. But here I just want to point out one reason. Whenever you do the modeling, let's say you have two parameters, okay, theta 1 and theta 2, and you basically are introduced with some data, and then you sample from, let's say, or even, let's not even start with the sampling problem, which gets things complicated. You just basically map the likelihood, okay, as a function of theta 1 and theta 2. You just produce a map of the likelihood, and you just look at this tail, okay? If you were to just claim that basically the ink here gives you the probability density at a given point, theta 1, theta 2. If you were to claim that your maximum likelihood solution is a good description of your probability function, then you would be wrong. That's because there's a fat tail here, and if you look at the marginal distributions, your maximum likelihood point, if you just trace back to it, does not actually reach the maximum volume of your posterior. Similarly in that case as well. Well, not so much here, but so much there because of the banana-shaped likelihood distribution here. So as a result, the takeaway message from this slide is that sometimes you just need to take into account such covariances, such banana-like shapes in your posterior, or when I say posterior, I just mean currently, I just mean the probability density function. So in order to take these into account, you have to be Bayesian. Okay, so far I've just defined a couple of terms and just motivated why we should be Bayesian in statistics. Now, one thing I did not mention when I just showed you the previous plot was so-called transdimensional covariances. This is something we usually sweep under the rug when we discuss statistics. That's simply because it's really hard to do this. In many models, or in many situations, I should rather say, and I will just motivate it directly with an example. Imagine that you are given, and again, let's go astronomical. So you are given an astronomical image, and for this problem's sake, I just chose it to be gamma rays, okay? So you are given a patch of the sky and the observation in gamma rays. Basically, every pixel is a Poisson process where you count photons. And then you are given the task of finding point sources in this image. And I just zoomed into a small patch of it, okay? And here, basically, the color scale, ink, shows you how many photons there are per pixel. So yellow being highest. So there's essentially an island here. And you are given the task of fitting for the point sources. Now, I think the very first thing you'll do is put a point source, single point source there, okay? That's the most obvious thing. Second, you might try 2 point sources that are slightly different, that are slightly separated. Third, you may start adding yet another source, the third source, just to be able to model that feature to the south. You may start moving the sources around. That's within model covariances. Again, by the way, the size is proportional to the flux of the point source, okay? So when I just change the size, you're just changing the flux of the point source. You can switch the labels. These are all operations you can do. Add yet another third source in this configuration, delete that, etc., and maybe add a fourth one, etc. So you can repeat this experiment many times, and every time you might actually get a consistency between your model and the data. Now the question is, which model do you choose? I'm sure when you actually model your data in whatever science you do, you come up with situations like this. And there's always a prescription to try to tackle this problem, such as Bayesian information criterion, Akaike information criterion, Bayesian evidence, etc. There are many ways, and I will just talk about yet another way, or some related way. Obviously, it's related to the Bayesian evidence. But just schematically, what's happening is, if you were to enumerate all the models that you could think of that I was just showing the previous slide, on the x-axis, and on the y-axis, you plot the likelihood, then there will be many configurations in which the likelihood will be very comparable between different models. And what's more important is that likelihood or log likelihood difference is going to be less than what you would normally need in order to formally detect something. Now, for the particle physicists in the audience, you usually detect something when you have 5 sigma. And there may be many situations where you might have models that whose consistency with the data or the log likelihood difference corresponds to a sigma that's less than 5 sigma. Which one do you choose? Now, in particle physics models, obviously, you don't have this situation of point sources, but you may have similar degeneracies. But in astrophysics, when you model images, that becomes even more crucial. So that's just a schematic way of showing this. There are a couple of terms. So these guys are then elements. So you're splitting and merging. These two models are different by basically a split merge. And that's basically what I usually refer to as the meta model, which is the space of all models that you could think of. Now, a couple of points about what I was just describing and what I usually refer to as traditional cataloging, but I don't think this is a common term, so I should probably define it. It's just basically taking frequentist statistics and applying it to a meta model. That's what I call a traditional cataloging. It does cause some loss of information. I think I've already discussed this because you're losing information about which model to choose, and if you were to be able to propagate your uncertainties, you'd be conserving more information about the data. And I already mentioned the second one. And third, just like the previous case, you cannot basically encapsulate non-Gaussian uncertainties. This is again some assumption usually that we kind of assume almost always that our uncertainties are Gaussian. And in the large sample limit, that's fine. But sometimes you're just not in that limit and you have to work in that limit. In some problems, you just cannot escape that. And then you have to be really careful about your statistics. Okay, so with that, I will just give an introduction to Bayesianism and how that's important, and then feed that into probabilistic cataloging, into the definition of the probabilistic cataloging. So I already mentioned that in Bayesian statistics, we redefine probability as degree of belief as opposed to frequency of occurrence. And that's basically the Bayesian, the Bayes theorem. And I think I have the term separate, so yeah. Okay, so you have this term that's called the prior. So basically that's the probability of observing a parameter given the model or under the model. That guy is the likelihood, which I already defined in one of the slides previously. That guy is called the posterior, which is the updated prior after the introduction of the data. And that's, again, a probability defined over the same object, theta sub n. However, now on the right-hand side, you also have data, as opposed to this guy. That's basically conditional on the data as well. That's the posterior. And there's yet another term, which I will define later. Now we come to probabilistic cataloging. Probabilistic cataloging is a trans-dimensional, threshold-free, Bayesian, and hierarchical inference framework to sample from the posterior of a meta model. Now, I know this is a loaded sentence. However, I think I've defined most of the terms here, probably except threshold-free. So threshold-free just means being independent of a particular detection threshold. I've already mentioned the 5 sigma threshold. That's common in particle physics. Other types of science may choose their own detection limit. Could be 6 sigma if you are uncertain about your systematic uncertainties, for example. If you are completely fine with your systematics, then you may be happy with 4 sigma. I don't know. But it's basically independent of that threshold, and it's Bayesian. I also have not defined hierarchical. Hierarchical, I think, is the list of your words here. It's not really important, but it's essentially just in a sentence. It means you reparameterize your priors in terms of other parameters, and we call those parameters hyperparameters. It's just a notation, so it's not really critical to the discussion. So I will skip that. Now, I will talk about MCMC, Markov chain Monte Carlo, real quick, for those of you who don't think about this every day. So in Markov chain Monte Carlo, what we do is we simulate probability density function. So sometimes there are many probability density functions that you cannot directly sample from. They're not analytical. So what you do is you construct a chain who has the Markovian property. By the way, Markovian property is the property of not depending on your history. So you construct a chain, and the current state of the chain does not depend on the history, or at least the probability density function of the current or the next state does not depend on the previous states. So the way you do this is you then propose changes from state to state. You start with some state, you propose a state to jump to yet another state, and depending on the log likelihood differences, you either accept or reject, and then you do this a million times, and eventually you get a posterior like this. Essentially, this posterior comes from the frequency of your visits to the different states. as a function of your parameter theta sub n. Now, what's different in probabilistic cataloging? This was good old MCMC. Now, I will define reversible jump Markov chain Monte Carlo. There's an insect. I keep hearing. Sorry. Reversible jump Markov chain Monte Carlo. This was actually published kind of recently for a mathematical framework. And the idea is to promote what I just described, Markov chain Monte Carlo, to a transdimensional space, in the sense that you are interested in jumps across different models, so models with different dimensionality. So here, for example, you have m sub n and theta sub n, and m sub n prime, where n prime doesn't necessarily have to be equal to n. And then you start sampling from this posterior. Now, this part, the within model proposals, and this part are the same, just like in the MCMC. However, this part is kind of interesting. It's new to probabilistic cataloging, where you either add elements to your model, or subtract or kill elements from your model, or split your elements or merge your elements into other elements so as to change their number. So, for example, if this was the point source problem, you'd be merging the point sources into a larger point source, or splitting them into smaller point sources, so as to kind of maintain the likelihood, so you can actually traverse the chain efficiently. That's the mathematical background of it. I won't really go into the acceptance ratios, etc., because this is not really a target audience for that. However, I'll just show you the output product. Basically, what you get is you get the good old posterior, and in addition to that, you get a posterior on n. That's the posterior probability distribution over the dimensionality n, given the data. That's a very valuable object. That is not available in good old Markov chain Monte Carlo. Now, some pretty movies. Sorry, it may get boring from time to time, but at least this one should be fun to watch. So what you're looking at is a simulated image. That's basically an X-ray image. So imagine you have an X-ray telescope. You've collected your photons, and then there are a bunch of point sources. So the brightest point source is here. The ink basically means number of number of photons per pixel after background subtraction. And then the green squares are the locations of the true point sources. I mean, this is a simulation, so you know the underlying truth. And for every frame, there are many frames in this animation. For every frame, blue data points or crosses are the positions of your model point sources, or in general elements. And at every step of your Markov chain Monte Carlo, you propose either within model changes, so you basically propose changes in position or flux, or you add point sources, subtract point sources, split point sources, or merge point sources, so as to traverse this meta-model space, this large space across models. And I will just zoom into a couple of regions of the same image. So here, for example, there are 1, 2, and 3 underlying sources. And if you look at the posterior, sometimes it's 2, sometimes it's 3. And that basically is the propagation of uncertainties across dimensions. Because now you might ask, why aren't there 3 model point sources at every time? The reason is, because there are background fluctuations due to the noise, and there's Poisson noise as well, the signal to noise is not high enough for you to say there are 3 point sources every time. In fact, if you had even smaller signal to noise, then your fluctuations would be even higher. And I will just give more examples. For example, this guy, that's a 0 or 1 question. There is a real source, but as you can see, the underlying pixels, they really don't contain many photons. So the point source, the model point source, is sometimes there, sometimes really not. So it's not really sure. So it basically gives you almost like a probability of existence of that point source. This is again a feature of doing transdimensional modeling. So this guy is a really bright one. And you see the blue cross almost never moves. It's almost always there. It never is killed. But doesn't even move. It does move slightly just because you have finite signal to noise, but it's almost fixed. And that's simply because there's so many photons associated with that point source. Now, I don't want to bore you with more stats, so I will just show you a couple of plots associated with the results of this pipeline called probabilistic cataloging. And then if you're done with the material, I might actually start the next lecture a little earlier so I can actually finish it because it's really loaded. So, but before we come to that, so this was basically from one of my PhD papers where I basically took the Fermi data and then using probabilistic cataloging compared the catalog I got basically with the underlying catalog that's produced by the Fermi collaboration using traditional cataloging. And obviously there was a nice match, which there should be, but then I basically tried getting the same result with a lower signal to noise, and that's, sorry, I actually put them in the backup slides, but if you basically lower the signal to noise, you still get the same picture. And that's the really nice thing about probabilistic cataloging is that because you conserve information, you can actually learn the same amount of information by having less data, or by a factor of 2 at most. Obviously, there's always a limit to everything. So just one idea about statistics I have to mention when I discuss probabilistic cataloging. Everyone probably knows Occam's razor, right? It's the fundamental approach in science where you have to make the least number of assumptions. Well, there is a projection of that in statistics. It's called parsimony, where if I were to give you, let's say, a bunch of data points with certain uncertainties and ask you to just draw a line to minimize the chi-squared, that is, maximize the consistency of your model with the data, you could just give me this. Now, if I were to ask you to give a better model, you might break your line into a couple of chunks and then re-minimize your chi-squared to get a better fit. If you really exaggerate, you can actually start doing this, and that's really not good. It's called overfitting. Because if now, after overfitting, if you resample the data, if you take another measurement from the underlying physical, from the universe, basically, you interact with the universe, get another sample, then you would be basically not predicting the new data point right, just because you overfit. So that's a dangerous thing to do. Now, with probabilistic cataloging, the way we implement this is through the Bayesian evidence. I have shown you this this term previously in the Bayes equation, and it was basically in the denominator. It's the probability of observing the data under some model. It's called the evidence, and it's essentially an integral over the likelihood times the prior times the differential. So essentially you take the likelihood and convolve it with the prior and integrate. That's the definition of evidence. And what it actually means in words is if your likelihood is really low across a large fraction of your prior space, then your evidence will be low. I'll just put this in a really nice figure here. So imagine there are 3 models, okay, and a data that you observe. So you enumerate the data on the x-axis, and the data that you happen to observe is called D, okay? And the 3 different models, M1, M2, and M3, try to predict this data. Now, M3 does a really bad job in predicting D. It's down here. It's almost 0. It's the Bayesian evidence. So it's out. We really don't like it. So we rule it out. Let's look at M2 and M1. M1, let's start with M1. M1 has a non-zero Bayesian evidence. So, okay, fine. However, M2 has a higher Bayesian evidence, and the reason why that is the case is because M2 predicts a more unique set of data. That is, the spread is actually lower in the data space. So in words, what this means is whenever you construct models, you better construct models that don't predict lots of data. you want to make unique predictions. That's true across all scientific methods, essentially. Whenever you don't make unique predictions, you are either here or here. So that's no good. Yes?
Do we have a kind of measurement to take the best model of all the? I mean, there could be one M4, which is like slightly better than M2.
Okay.
And how can we choose M4? It is slightly better than M2, but it's not overqualified.
Well, I think what you would do, you would just be comparing the Bayesian evidences, and you would be taking like whatever has the highest Bayesian evidence for the data that you observe. So if there were an M4 that touches this and then goes directly down, then you'd be selecting M4. Other questions? Okay. And I will just skip this because I am running out of time. Okay, one more thing. So regularization. I think I've mentioned that parsimony is a really important thing in statistics, because if you don't follow parsimony, then you overfit or underfit, in which case you don't have a good model anyways. So either underfitting or overfitting is no good. However, there is some wiggle room about this ideal fitting that I've mentioned. And for a Gaussian problem, the way you obtain that ideal fitting is you penalize your model by chi-squared of unity, or in log likelihood space, half per degree of freedom. This is something that you all know. I'm just putting it in statistics language, because I think whenever you do fits, for those of you who work with data, you always fit, for example, for reduced chi-squared, right? Reduced chi-squared is chi-squared per degree of freedom. And chi-squared obviously assumes Gaussian noise. So basically, whenever you minimize chi-squared degree of freedom, you do this same penalization. However, this basically makes it explicit, and you can actually you have a wiggle room around it for various different problems with different error characteristics. So in PCAT, or probabilistic cataloging, we basically apply the same prior. However, we do have a free factor in front, just in case we say, for example, have Poisson likelihood as opposed to Gaussian likelihood, or any other likelihood. And I think I will again skip this because I really don't have much time left. I'll just give a couple of examples from here and then call it a day. Okay, so I mentioned the name probabilistic cataloger. There's essentially an implementation of probabilistic cataloging called probabilistic cataloger. It's basically a Python-based, fast, very user-friendly, customizable Python implementation that lives on my GitHub, and it's been published through 2 different papers. If you're interested, come talk to me. This is the probabilistic graphical model associated with it. PGM is basically a map that shows the relations between probabilistic variables. So this blue node is a parameter, and it's the dimensionality of the green dots, which are, depending on whatever model you have, might be, let's say, the x-coordinates, the horizontal coordinates, the vertical coordinates, the fluxes, the colors of your point sources, as well as other parameters in your model. Some may be characterizing the point spread function. Some may be characterizing the background, the level of the background. However, at the end of the day, you forward model them to get the model image, and then you make the comparison between the data and the forward model through the Poisson likelihood. So that's the probabilistic graphical model associated with it. And that's basically how you interact with PCAT. I'll skip this, really running out of time. And yeah, okay, so this was just the plot I basically meant to show in the beginning. So you remember this plot when basically this is essentially on the y-axis, that's the fluxes that you get for each point source in the northern region of the galactic, in the northern pole rather of the galactic plane, and on the x-axis those are the fluxes of the point sources published by the Fermi collaboration. You see the nice x is equal to y correlation. And if I now show you basically data with undersampled data by a factor of 2, you still get the correlation. And if I undersample by a factor of 4, you almost see the correlation again. So that means probabilistic cataloging is doing as good as traditional cataloging by undersampling the data by a factor of 4. That's basically a power that is unlocked by doing the transdimensional inference at the faint end mostly. At the bright end, you don't care because there's enough data anyways. With that, I'll just conclude and get questions. So I'll try to be faster in the second lecture because we have a lot to cover. So I'll stop now, and if you have questions, I can get some. Yeah.
Sorry, doesn't all the probability distributions become Gaussian when n is large?
Yes,
So
but n is different from that n. Here, my notation n is the number of free parameters. Your n is the number of data points. Yeah. Yes.
Is there a way to calibrate our models such as precise and accurate things? If our method is, the band is a bit smaller, we can calibrate it to give the
Not sure if I understand. Like calibrate what really?
MABAS. I'll ask it later.
Okay. Yeah. I'll be around.
Okay, suppose the value of the n is 10, and among them maybe the 3 parameters are degenerate. So I can
Yes.
actually explain the same probability distribution function by increasing or decreasing. So how it will reflect in my
Right.
I can predict the data.
So in Bayesian statistics, when you sample, you marginalize over them. So if there are covariances like banana-shaped or even more funny shapes, then what you would be doing is you would be marginalizing over them, and you wouldn't really care if there are degeneracies, because what you really care is the probability distribution of whatever the marginalized quantity you are interested in. So that, by the way, is a general statement that's true even for non-PCAT stuff. With PCAT, what we marginalize over is actually, so just to give you the complete story, what I just described is common to pretty much all the methods in statistics. What's new here is we are able to marginalize over n. That's the idea. Because when you are able to marginalize over n, let's say you're interested in measuring the background level, and you really don't care how many point sources there are in your image. You can marginalize over this guy, those guys, your PSF, and you can produce P of A given the data, marginalize over the meta model. That's the idea.
And what about the making mock catalogs? I don't know.
Mock catalog, you draw from some underlying distribution.
So random distribution, I mean.
Sorry?
It will be random distribution?
Yeah, but when I say mock, I mean forward modeling, so for simulating.
Oh,
Yeah.
thanks.
What is the trade-off between probabilistic and traditional cataloging?
Speed. Probabilistic cataloging obviously has advantages and also disadvantages. The disadvantage is that you increase the computational complexity of the problem, and it gets worse the fainter you go. For example, if you try to sample from one sigma fluctuations in your data, then it becomes exponentially slower to actually converge your posterior. If you have the computational power to spend, then it's the method to use. But in many problems, this may not be the case. Okay, so no more questions. Let's give a break, and then we'll continue with the next lecture.